Hey Rock Buds, more rocks coming. Okay, first rock of the day here. Let's just have a look. Do you see what I see? What does that look like? Does that look like a shell? Piece of a shell? Let's look for some more stuff like that. Whoa. Look at that. So basically, a white rock with no visible mineral crystals, but little hunks of shell. What do you think? Let's do the limestone test with 5% HCl solution. Ooh, yeah. So no brainer. This is limestone, but it's young limestone. In other words, excuse me, it has not been subjected to the kind of physical pressure from the weight of sediments on top of it that are going to mash it into a more compact state. And also that's going to eventually mash out the pieces of shell so that they're unrecognizable, and it's going to turn the whole thing kind of grayish. Okay, this came from the coastal plain of Georgia, inside a concrete, a mine that mines limestone to use as in concrete. So let's see what this is going to turn into eventually. It's going to kind of look like this, be grayish with some white streaks. Let's test that with the acid. Yeah, see, that's the same reaction. And this is limestone. Limestone that's from the. It could be from the Cambrian period, rift to drift sequence. And I'm just going to say that's where it's from, plus or minus. I don't remember where I got it, but it's definitely limestone. This is what that whitish stuff will develop into: young limestone and old limestone. Here's our next rock. And this is a rock that a buddy of mine cut into slabs with his rock saw so that we could really get a good view of it. So what do you see? Well, I'm going to wet it a little bit. There we go. Do you see mineral crystals? Yes, we do. And I see dark ones and light ones. Do you see little mirror specks in there? Okay, what are we going to call that? Mirror muscovite, yes. Do you see clear or gray spots in there? I do. Let's look at the other side. Clear gray spot. Some more of that clear gray stuff. There's a nice one right there. So what do we call the clear or gray stuff? That's right, quartz. Quartz is always clear or gray in a rock. And incidentally, that's pretty cool because they have found, I don't know how recently it was, but they found in Antarctica, they found that the quartz, the clear or gray quartz crystals in rocks form a protective barrier to the cold, but lets light in so that algae, little tiny algae can grow under there, which is pretty cool. I also see some yellowish, whitish yellowish stuff. What do you think that's going to be? Right, that's going to be some kind of feldspar. It could be potassium-rich feldspar or sodium-rich feldspar or a combination thereof. But since I don't see a lot of pink, which tells us for sure potassium feldspar, then let's just assume this is mostly sodium-rich feldspar. So, by the way, what's the black stuff? Let's figure it out. Remember we said that if a nickel can scratch the black stuff, then it is what? Right, biotite. So let's do that. Okay, and see we got some gray dust there. That tells us that the nickel does scratch this black stuff. So that means it's biotite. So we have quartz, probably sodium-rich feldspar, and biotite, and a little bit of muscovite. So is this a felsic rock, an intermediate rock, or a mafic rock as far as its Bowen's reaction goes? Excuse me, if you said it's an intermediate rock, I think that would be right, because it's got a lot of biotite in it. And assuming that the feldspar is sodium-rich feldspar, and I believe it is, sodium-rich feldspar and biotite are both minerals that make intermediate rocks. Okay, so it's intermediate rock. Also, it's easy to see that there are bands in this rock. It's got dark bands and light bands. What does that tell you? Right, if it's banded, more than likely it's a metamorphic rock. So we have an intermediate reaction, metamorphic rock that has basically it's similar minerals to granite, but it's a little bit more mafic than granite. So what are the possibilities? What do you think? Well, there's only one possibility that I can think of, and that is biotite gneiss. Biotite gneiss, a metamorphic rock that has a lot of biotite in it. And that's what this is. There's huge amounts of this biotite gneiss in both the inner Piedmont geologic terrain, which was an island arc, and in the eastern Blue Ridge geologic terrain, which was island arc material plus sediment, ocean sediments. Think of Black Rock Mountain State Park in Georgia. Black rock means biotite gneiss. Also, there's a lot of it in the Carolina geologic terrain, which was a Devonian era microcontinent that smashed. So, what is the protolith of biotite gneiss? And what does protolith mean? That means what rock became biotite gneiss after it was metamorphosed? What rock was metamorphosed and that turned it into biotite gneiss? Well, the most likely candidates that I can think of are intermediate igneous rocks. So our intermediate igneous rocks, we've got an underground version of intermediate igneous rocks, and that's diorite. We've got an above ground version, that's andesite. So biotite gneiss could be most likely is the metamorphic version of one of these rocks, either diorite or andesite. By the way, andesite reminds me of the Andes Mountains because there's a lot of it in there. I don't know if the Andes were named after andesite or if andesite was named after the Andes. Probably the andesite was named after the Andes Mountains. So where do diorite and andesite come from? They are most prevalent in subduction zones. Ocean crust gets subducted beneath land crust, and a lot of ocean water goes down, and that facilitates something called fractional melting, where the magma, that the ocean crust that melts, fractions into felsic, intermediate, and mafic magmas and lavas. And then later on, continental crashing will push that the diorite and andesite that are formed via subduction into a metamorphic rock called biotite gneiss. So there you have it, biotite gneiss. Here's our last rock for this time. Do you notice anything about this rock? Well, I noticed that it doesn't have, I can't see mineral crystals. If they're there, they're teeny tiny. I also notice that it's kind of greenish in color. And if you've ever eaten pistachio nuts, then we could say this is pistachio green. And since it's pistachio green, there's only one rock, or let's just say mineral, that geologists talk about as being pistachio green. Do you know what it is? Yes, it's epidote. Epidote. So this rock is chock full of epidote. And geologists would call this epidote granophyls, which is a weird name, granophyls. Seems like it's plural, but should be plural with granophyls, but it's singular. It's a singular rock. Granophyls is a rock that has you can't see the mineral crystals in it. It's kind of homogeneous in its structure. And so this is epidote granophyls. It is a mafic rock. Epidote is a mafic mineral. And where does epidote come from? It comes from the metamorphism of mafic rocks, the minerals in mafic rocks. So we're talking sodium, calcium, feldspar, also pyroxene. They can morph into epidote given certain conditions of metamorphism. And also we know that these two minerals, sodium/calcium, feldspar, and pyroxene, come from mafic rocks, especially lava, basalt lava, gabbro pluton. So this epidote granophyls came from the Carolina terrain, geologic terrain, and began as a microcontinent that crashed into North America way up high, New York, Pennsylvania, and even higher up. Back during Devonian time, it shed all its sediments off in that area, the Catskill Delta. We talked about that. And then it slid down along various faults, including the Brevard Fault Zone, to Georgia and South Carolina. Maybe some in North Carolina, too. And all these metamorphic processes resulted in the basalt lava, gabbro pluton, associated with the Carolina terrain, being metamorphosed into epidote. Epidote is high in calcium and magnesium, and so this rock came from an area in the Carolina terrain not far from here, where there were huge amounts of redbud trees growing. And a redbud tree is, if you see them in mass, they're an indicator of high calcium/magnesium soils. Okay, epidote. The last rock is a weird one. This rock, oh, look at that. Looks like a quartz vein. Yeah, it runs kind of all the way through there. So you've got this very pitted, brownish, irony-looking matrix that has these quartzy-looking crosshatch veins running through it. Now, this rock came from the Cumberland Plateau, a sandstone formation called the Castle Rock Formation. And like if you go up to the Big South Fork National Recreation Area up in Kentucky, Tennessee-Kentucky border, you can see some of this rock. And this is called boxwork, which is weird. Boxwork now. Boxwork is the way it looks. It looks like you've got these boxy-looking edges with holes, like boxes, I guess. So how does this boxwork form? Boxwork forms in a couple of situations that I can think of. First of all, in the sandstone of the Pennsylvania Sandstone Formation. Let's talk about what that was. When Africa crashed and began to shed its sediments, huge amounts of sand flooded over covered the land in a layer that moved from east to west, and then streams ran through this, and the sandstone was mineralized when quartz came in carrying iron, lots of iron deposits. The iron infiltrated the sandstone brought in by these quartz veins, and then over time the sand eroded out. But this irony material is a little harder, and so you get this boxwork pattern. I'm supposing this irony stuff is hematite. I don't really know. Another place that boxwork forms is in caves. If you ever go out to South Dakota to Wind Cave National Monument or National Park, Wind Cave has more boxwork in it than any other cave in the world, I believe. And in that case, boxwork forms when calcite-laden water forms cross-hatching of ridges along the cave walls and sides that looks just like boxwork. So that's boxwork. And this kind of brings up the question. It brings up the idea that there are three mineral/elements that are ubiquitous in the ground and rocks in the soil. One is quartz. Quartz is a water-laden quartz flows through so many rocks. Like the gold deposits of Dahlonega and other places. The quartz-laden water picks up the gold and the quartz and deposits it in these big quartz veins and rocks. So quartz is ubiquitous; it's everywhere. Another one is iron, and this boxwork is an example of that. Iron is everywhere in the ground because that's one of the major components of volcanic rocks. It's mineralized into all kinds of other rocks. And then finally, calcium carbonate, which is the main product of limestone. That's as another ubiquitous mineral that gets into all kinds of places. Okay, boxwork. Okay, guys, that's it for now. Are you as glad as I am that spring is here? So, happy rock hunting. Pop out.